Imagine a world where the rules of quantum entanglement, a phenomenon that has left scientists baffled for decades, are finally cracked. A new study has made a groundbreaking discovery, revealing that quantum entanglement follows the same basic principles across all dimensions. But here's where it gets fascinating. This breakthrough has the potential to revolutionize the field of quantum computing, secure communication, and error correction. The team of researchers, led by Yuya Kusaki of the Kyushu University Institute for Advanced Study, used a tool called thermal effective theory to pinpoint universal behavior in a precise limit. This matters because quantum entanglement is the backbone of quantum computing, and theorists have been chasing a clean understanding of it for decades. So, what does this mean for the future of quantum technology? Let's dive in and explore the intricacies of this phenomenon. The study proves that a standard measure called Rényi entropy has a universal form when the replica number n is small and the boundary of the region you study is spherical. In plain terms, the small n behavior depends on a single constant from the effective theory and on the area of the region's boundary. This combination holds in any number of spacetime dimensions that admit a conformal field theory description. But what makes quantum entanglement so crucial? Most exact results about entanglement come from systems with one space dimension plus time. Moving to higher dimensions complicates everything because shape, curvature, and boundary effects start to pull their weight. However, many quantum systems obey an area law, where entanglement scales with boundary size, not bulk volume, and this feature underwrites efficient simulation strategies in practice. The new paper strengthens the theoretical footing for that kind of scaling in a controlled limit. By nailing down which parts are universal and which parts are model-specific, the authors also map where numerical methods might safely cut corners. That saves time and reduces the chance of chasing artifacts. So what's the role of Rényi entropy in all this? Rényi entropy is a family of numbers that summarize how a quantum state spreads its weight across possibilities. The label n is the replica number, and different n emphasize different parts of the distribution. For entanglement, we compute Rényi entropies for a subregion A to see how strongly it links to everything else. From those values, you can extract the entanglement spectrum, which is the set of effective energy levels for the reduced state. Those levels come from the modular Hamiltonian, the operator whose exponential gives the reduced density matrix once you normalize it. Large eigenvalues of that operator control fine structure in the spectrum, and, by extension, the way information is encoded. But here's where it gets controversial. The study uses thermal effective theory, which treats a complicated quantum field theory as if it were a simpler thermal system, but with a carefully chosen set of parameters that capture the key physics. Some might argue that this approach oversimplifies the complexities of quantum entanglement. Others might see it as a necessary step towards a deeper understanding of the phenomenon. What do you think? Should we be embracing this new approach, or do you think it's a step in the wrong direction? The approach also separates bulk contributions from boundary terms, and it shows how boundary effects slip in one order lower in n. That hierarchy helps clarify which pieces are robust and which are sensitive to details like surface curvature. How do 2D systems differ from their higher dimensional counterparts? Two-dimensional systems often allow exact answers thanks to symmetry, and the small n story here connects to a stronger result that holds for all positive n. In 2D, you can use a hot spot trick that focuses on regions where the effective temperature soars, and the method delivers full n formulas. The new paper explains why that trick stops working the same way in higher dimensions. Curvature and derivatives of the effective temperature do not stay small near the boundary, so higher-order terms refuse to be ignored. That does not spoil universality in the small n limit, which remains intact. It simply draws a clean line between what 2D symmetry guarantees and what higher D physics permits. So, what's the bigger picture here? Sharper control of Rényi entropies can guide tensor-network and Monte Carlo methods for many body systems, especially when geometry matters. If you know which terms dominate at small n, you can target algorithms and set error bars with more confidence. There is also a bridge to gravity. Rényi entropies play an active role in holographic calculations that relate quantum field theories to gravity in higher dimensional spacetimes, where a geometric prescription translates entropies into areas of special surfaces. The work hints at new classification ideas for phases of matter, since universal data tied to shape and boundary can act like fingerprints. It may also sharpen the language we use to compare quantum simulators and real materials without getting lost in model-specific weeds. The study is published in Physical Review Letters. As we continue to unravel the mysteries of quantum entanglement, we may uncover even more surprising insights that challenge our understanding of the universe. What are your thoughts on this breakthrough? Do you think it will pave the way for a new era in quantum technology, or are there still too many unanswered questions? Share your thoughts in the comments below.